introduce our next speaker, who will continue to talk about divisible design graphs. So for this special session on association scheme, we have two exceptional talks on divisible design graphs. And our next speaker is Dmitry Panasenko, so you're welcome.
At first, I would like to thank the organizers and all the participants here. And it is actually the continuation of my talk on the previous, the 5th workshop. And so it's called More About Vertex Connectivity of Special Classes of Divisible Design Graph. There is quite a bit special meaning in this title. I think you will see what I mean in a few slides. So let me recall some definitions at first. So Deza graphs were introduced in 1999 as a generalization of strong regular graphs. A K-regular graph on the vertices is called a Deza graph with parameters Vk, Ba, where B is more or equal to A if the number of common neighbors of any two distant vertices takes just two values, A or B. A Deza graph is called a strictly Deza graph if it has diameter 2 and is not strongly regular. And a K-regular graph on V vertices is called a divisible design graph with parameters Vk, lambda 1, lambda 2, Mn, if its vertex set can be partitioned into M classes of size n, such that two distinct vertices from the same class have exactly lambda 1 common neighbors, and two vertices from different classes have exactly lambda 2 common neighbors. The definition implies that divisible design graphs are Deza graphs. Divisible design graphs were first studied in master theses by Meilenberg in 2008. And in 3 following papers, such graphs were studied in more details, and a lot of new constructions were presented. So as you see here, the paper with number 4 by Hadamard and Cirkolich is called More About Divisible Design Graphs. So it's a little homage to this paper. Divisible design graphs have at most 5 distinct eigenvalues, and formulas for eigenvalues and their multiplicities are presented in the table below. And the vertex connectivity of the graph gamma is the minimum number of vertices whose deletion from gamma disconnects it. For example, the vertex connectivity of a strong irregular graph is equal to its valency, which was proved by Brouwer and Messner in 1985. A similar result for distance regular graphs, so in a sense, more general result, was proved by Brouwer and Kulin in 2009. Let x and y be two different vertices of a graph gamma. Two simple paths connecting x and y are called disjoint if they have no common vertices different from x and y. A set of vertices S disconnects x and y if x and y belong to different connected components of the graph gamma minus S. A set S of vertices of the graph gamma is called disconnecting if it disconnects some two of its vertices. So there is a result on vertex connectivity of Deza graphs, which can be obtained by dual Zeta switching. So let delta be a Deza graph obtained from a strong regular graph with restricted RNS by dual Zeta switching when we have one of the following two cases. If R is not equal to 2, then the vertex connectivity of delta equals to its valency, except for the case when gamma is a complement to n times n lattice. In that case, vertex connectivity is 1 less than valency, or R equals 2. So anyway, let me remind the result of the previous talk. So there will be 4 lemmas. The vertex connectivity of a connected DDG gamma with parameters Vk, lambda 1, lambda 2, Mn, where lambda 2 equals 0 equals k. So it equals the degree of the vertex. The vertex connectivity of a connected DDG gamma with parameters where lambda 1 equals k, so again, the degree of the vertex. Lemma 3, let gamma be the degree with parameters where lambda 2 equals to k minus v, then the following statements hold. If lambda 1 does not equal to k minus 1, then the vertex connectivity of gamma equals k. If lambda 1 equal k minus 1, then the vertex connectivity of gamma equals k minus 1. So this case is a little bit different. And the vertex connectivity of DDG gamma with parameters where lambda 1 equals k minus 1 and lambda 2 not in 0 or doesn't equal 0 to k minus v equals k minus 1 again. So actually all DDG with lambda 1 equals k minus 1 actually have vertex connectivity equals k minus 1. And now here we consider one construction of divisible design graphs. An M times M matrix H is Hadamard matrix if every entry is 1 or minus 1, and H times H transpose equals M times the identity matrix of the same size. A Hadamard matrix H is called graphical if H is symmetric with constant diagonal, and regular if all row and column sums are equal. So construction, consider a regular graphical Hadamard matrix H of order L square at least 4 with diagonal matrix -1 and row sum L. The graph with adjacency matrix A, you see here, where M is this block matrix, so J actually is a matrix of ones of the same size as H, and then is this block matrix, is a DDG with parameters 6L squared, 2L squared plus L, L squared plus L, L squared plus L divided by 2, 3, and 2L squared. So let us call such a DDG gamma, and we fix the case where L is positive. Consider the subgraph induced by the first 2L squared vertices of gamma. In terms of construction, this subgraph has adjacency matrix M, and the subgraph induced by the last 2L squared vertices of gamma. In terms of construction, this subgraph has adjacency matrix N. Denote by gamma 1 and gamma 2, the first and the second subgraph respectively. So actually it was showed in a previous talk that gamma 1 is a L squared plus L regular graph and gamma 2 is an L squared regular graph, and the vertex connectivity of gamma is at most 2L squared. And actually now I present some new result. So if vertex connectivity of gamma 1 is at least L squared, and vertex connectivity of gamma 2 is no less than L squared minus L, and the sum of these values is at least 2L squared, then the vertex connectivity of gamma equals 2L squared. So let me present a sketch of the proof. Denote by gamma 0 the cyclic induced by 2L squared vertices of gamma that correspond to the middle rows and columns of A. Note that any vertex from gamma 1 has exactly L squared neighbors in gamma 0, and any vertex from gamma 2 has exactly L squared plus L neighbors in gamma 0. Let T1, T2, and T0 be non-negative integers such that their sum is less than 2L squared. If T1 is more than vertex connectivity of gamma 1 and T2 more than vertex connectivity of gamma 2 or equal, then T1 plus T2 is at least 2L squared, which contradicts the inequality. So this case is excluded. Denote by gamma 1 hat, gamma 2 hat, and gamma 0 hat the graphs obtained by deletion of T1, T2, and T0 vertices from gamma 1, gamma 2, and gamma 0 respectively. And also denote by gamma hat the graph obtained by deletion of T1 plus T2 plus T0 vertices from the gamma itself. There are 3 possible cases. So case 1, if when both T1 and T2 are less than vertex connectivity of gamma 1 and gamma 2, when both gamma 1 hat and gamma 2 hat are connected graphs. Thus, if there is at least one vertex in gamma 0 hat that has neighbors in both gamma 1 hat and gamma 2 hat, when gamma hat is connected, let us show that such vertex exists. Since gamma 2 is an L squared regular graph, we have the inequality that its vertex connectivity is no more than L squared, and consequently T2 is less than L squared. Since L squared is less than L squared plus L, which is the number of neighbors in gamma 0 for any vertex from gamma 2, we conclude that any vertex from gamma is adjacent to at least one vertex from gamma 2 hat, so the graph with deleted vertices. This means that any vertex from gamma 0 hat is adjacent to at least one vertex from gamma 2 hat. And there are two subcases for T1. The first is T1 less than L squared, and the second is T1 is more or equal to L squared. If T1 is less than L squared, an argument similar to the argument above implies that any vertex from gamma 0 hat is adjacent to at least one vertex from gamma 1 hat. So there exists a vertex, actually any vertex, from gamma 0 hat that has neighbors in both gamma 1 hat and gamma 2 hat. If T1 is more or equal to L squared, then the inequality is T1 plus T2 plus T0 is less than 2L squared, and T2 is at least 0, imply that T1 is less than L squared, which is the number of neighbors in gamma 0 for any vertex from gamma 1. Therefore, any vertex from gamma 1 is adjacent to at least one vertex from gamma 1 hat, and gamma 0 hat. So there exists a vertex from gamma 0 hat that has neighbors in both gamma 1 hat and gamma 2 hat. And case 2 is that T1 is more or equal to vertex connectivity of gamma 1, and T2 is less than vertex connectivity. Then gamma 1 hat is disconnected and gamma 2 hat is connected. Thus, if for each connected component of gamma 1 hat, there is at least one vertex in gamma 0 hat, having neighbors in both this complement and in gamma 2 hat, then gamma hat is connected. Let us show that such vertices exist. Since T2 is less than vertex connectivity of gamma 2, which is less than L squared, any vertex from gamma 0 hat is adjacent to at least one vertex from gamma 2 hat. Actually, it's like in the case 1. Since T1 is more than vertex connectivity of gamma 1, which is more than L squared, and T2 is at least 0, the inequality T0 less than L squared holds. So any vertex from gamma 1 hat is adjacent to at least one vertex from gamma 0 hat. Actually, the similar case was considered in case 1. So for each connected complement of gamma 1 hat, there is a vertex from gamma 0 hat having neighbors in both this complement and gamma 2 hat. And the case 3, where we change the inequalities, so T1 is less than vertex connectivity of gamma 1 and T2 is more than vertex connectivity of gamma 2, is actually similar to case 1 with the same arguments. So we proved this nice property. And now we consider a special case of this construction. If H1 and H2 are Hadamard matrices, so is the Kronecker product also a Hadamard matrix? Moreover, if these matrices are regular with row sum L1 and L2, respectively, then the Kronecker product is regular again with row sum L1 times L2. And similarly, the Kronecker product of two graphical Hadamard matrices is graphical again. Consider regular graphical Hadamard matrices H and H prime, as you see on the screen, and denote by H1 the matrix H. And for any integer t that is more than 1, denote by HT the Kronecker product HT minus 1 and H prime. The matrix HT is a regular graphical Hadamard matrix for the 4 to the power t with diagonal matrix minus 1 and row sum 2 to the power t. Applying construction 1 to HIT, we obtained a DDG with parameters you can see on screen, such parameters. And the smallest example is a DDG with parameters 24, 10, 6, 3, 3, 8. And the adjacency matrix, you can see here, where D is all ones matrix minus 1, and I is identity matrix, 0 is, O is a matrix of zeros. So actually we can rewrite this Kronecker product and the application of construction 1 to the matrix HT as a recursive construction. So we change D as this 4x4 block matrix, I as this 4x4 block matrix, and O as this 4x4 block matrix. And we get a recursive construction of the DDGs with such parameters. Let us denote such DDGs as gamma T. And let us consider two subgraphs as we considered before. So the first vertices gives us gamma 1t, and the last vertices give us gamma 2t. So actually it's the same subgraphs, but in terms of this application of the construction. Each vertex from gamma t can be associated to the corresponding block row of the adjacency block matrix, and two blocks from distinct block rows are called a pair if they lie in the cell block column. And actually, we're now going to count at first the common neighbors in gamma T. So actually, if the vertices associated with the same block row, when each block D gives 2 common neighbors and each block I gives 0 common neighbors. If the vertices associated with distinct block rows, then there are 2 subcases. If the vertices correspond to the rows with the same index within their block rows, when each pair D and D gives 3 common neighbors, each pair I and I gives 1 common neighbor, and all other possible pairs gives 0 common neighbors. If the vertices X and Y correspond to rows with different indices within their block row, then each pair D and D gives 1 common neighbors. Each pair I and I gives 0 common neighbors. Each pair D and Y or I and D gives 1 common neighbor, and all pairs with block O gives 0 common neighbors. And now we investigate how the replacement of blocks in the recursive construction affects the adjacency block matrix of gamma T. And investigation, we exclude all cases related to block 0. So for a block row in the recursive construction, each block D gives 3 new blocks D and 1 new block I. And each block I gives 1 new block D and 3 new blocks I. So it follows directly from this replacement. And now we consider 2 distinct block rows in the recursive construction of gamma T, and there are 3 cases. So if 2 distinct block rows are obtained from 1 block row with the replacement, when we have this pairs, so each block D gives us such pairs and each block I gives such pairs. The second case, if 2 distinct block rows are obtained from 2 distinct block rows and have the same index within replaceable block row, that's the one case, and you can see all possible pairs here in case 2. And the case 3 is 2 distinct block rows that obtained from 2 distinct block rows and have different indices within replaceable block row H. This is the third case. And you can see here all possible pairs. So it follows directly from this reconstruction and the construction itself. And actually, now I want to talk about the structural description of our subgraphs gamma 1t and gamma 2t. So gamma 1t is a divisible design graph with parameters you can see here, and you can see that this is a divisible design graph with k equals lambda 1. So how we can prove it? The graph gamma 1, 1 has adjacency matrix. So you can see here, so 4D blocks. And for gamma 1t, a recursive construction similar to this one can be applied. And we denote by A1t the adjacency block matrix of gamma 1t, and note that this matrix does not contain a block O. So the following table shows the number of blocks in each block row of the adjacency matrix according to lemma 9. So we just apply lemma 9 and we have this formula for number of blocks D and number of blocks I. And actually note that given a block row in A1t, there is exactly one block row that is equal to the given one, that is the block row with the same sequence of blocks. So in the next table, we show the number of pairs of blocks in two distinct block rows according to lemma 10. The case of equal block rows is excluded except for t equals 1. So you can see here it's the only possible case are two distinct block rows. Note that this table represents each of the cases from lemma 10. So all cases give the same number of pairs. And we just apply the formulas for lemma 2, and we have this nice number of pair of blocks. And after we apply lemma 8 to count the number of common neighbors for all possible cases, with having in mind this table and this table, we can show that gamma 1t is the DDG with parameters, such you see on the screen. And in particular, any pair of vertices corresponding to equal rows of the adjacency matrix forms a block of size 2 of the canonical partition. And this similar approach gives us the result for gamma 2t. So gamma 2t is a DDG with parameters. And note that in this case, lambda 1 equals 0. So this gives us an interesting series. There are two known DDGs of diameter 2 with lambda 1 equals 0. Or more generally, there are two known strictly Deza graphs with A equals 0. One on 8 vertices and one on 32 vertices. The series of gamma 2t covers both cases actually, and gives an infinite series of DDGs of diameter 2 with lambda 1 equals 0, and more generally strictly Deza graphs with A equals 1. So recently before our enumeration project with Leonid Shalaginov, there was known only graph on 8 vertices. When we discovered graph on 32 vertices, and actually this construction, or recursive construction, gives us an infinite series of such graphs. So lemma 13 is actually a reinterpretation of proof that was used in paper about vertex connectivity of Deza graphs, which obtained by dual Zadar switching from strong to regular, and it can show us such a result. Let gamma be a connected Deza graph with parameters Vk be A, with the second largest eigenvalue Q, and if gamma has a disconnecting set of minimum cardinality that is not the neighborhood of some vertex, then the following inequality holds: K minus 2Q is less or equal to the parameter B. So let us use this lemma to calculate vertex connectivity of gamma 2t. First, we calculate the spectrum of such graph as a DDG. So it has 4 to the power t plus minus 2 to the power t and 0 as its eigenvalues. And the second largest eigenvalue of this graph is 2 to the power t. And if we consider gamma 2t as a Deza graph, we get that parameter b equals to 4 to the power t minus 1. So the inequality from lemma 13 becomes 4 to the power t minus 2 times 2 to the power t is less or equal to 4 to the power t minus 1, which holds only for t equals 1. Thus, for any t more than 1, the vertex connectivity of our graph equals k, where k is 4 to the power t and the degree of the vertex. And if t equals 1, then this graph is the DDG with parameters 8, 4, 0, 2, 4, 2. By computer calculation using stage math, the vertex connectivity of this graph equals 4, which is the degree of the vertex. So everything goes as we think. So the vertex connectivity of all graphs from this family equals 4 to the power t. And the last result, so the vertex connectivity of gamma to the power t equals 2 times O to the power t. We just apply the result obtained in lemma 4. So by lemma 2, the vertex connectivity of gamma 1 to 2 equals the degree, which is 4 to the power 2 plus 2 to the power 2. By previous lemma, the vertex connectivity of gamma 2t equals 4 to the power t, and was by lemma 7. So the lemma about vertex connectivity of graphs from construction 1, we have that vertex connectivity of gamma t equals 2 times 4 to the power t, which is actually 2 to the power t less than the degree of the vertex. So we can have a divisible Deza graph with vertex connectivity less than any power of 2. And there are more construction of regular graphical Hadamard matrices with positive L. So in view of construction 1, there are more DDGs whose vertex connectivity is less than k, where k is the degree of the vertex. In this talk, we focused on the smallest graph from construction 1 and its generalization. We are interested if there exist examples of DDGs whose vertex connectivity is less than k, besides the graphs that can be obtained from construction 1, and besides graphs that with lambda 1 equals k minus 1. So we don't know at this time, are there any other constructions that gives us DDGs with vertex connectivity less than the degree of the vertex? There are some approaches for obtaining more general results about vertex connectivity of graphs. For example, the approach that was used in paper about vertex connectivity of strong regular graphs and paper about vertex connectivity of Deza graphs, or the approach that was used in paper about vertex connectivity of distance regular graph. Since the spectrum of DDG is not completely determined by its parameters, the first approach can only be used in specific cases like lemma 14, and we can have results, but such cases are not really well presented. The second approach requires more detailed consideration and possible development of new tools to apply to DDGs. We're interested if general results can be obtained for DDGs using both known approaches, and we'll try to obtain such results in the future. That's all. Thanks for your attention.
Okay, thank you, Dmitry, for the very interesting talk on divisible design graphs. Are there any questions to the speaker?
If there's no other question, can you please go back to lemma 12? And actually, it's not only 12, but is t is not necessarily odd, right?
Yeah, it can be even or odd.
So do you know, or can you give me a simple example where t is 2?
Graph where t equals 2?
Yeah, so then we have...
actually...
Oh no, it's there already.
Yeah, it's there. It's there
yeah.
on 32 vertices.
That's right, yeah. Oh, sorry, yeah, I overlooked it. Okay, so then my question is, can you give me an example for t equals 3?
It's just a recursive construction. We have, so let me rewind a bit. So actually the smallest graph has adjacency matrix DIID.
Yeah.
Apply this replacing 2 times, and you have a graph with where t equals 3, 4 times t it equals 4, and so on.
I see. Okay, I overlooked that. Yes.
I see. So
it's a bit over informative. I think if you the presentation will be available, so you can look at it in more detail.
Right. Well, but the construction is recursive, right? Yes. So you
yes,
can
yes.
I see. I see. Okay. Are there any other questions to the speaker? Well, if not, then let us thank again Dmitry for this remarkable talk. Thank you very much. And our next speaker